Okay. I understand the previous lecture might have been pretty pretty intense. Introduce a lot, reintroduce us a lot of concepts in different forms, different styles. Uh, and so I do hope to leave you all a bit of time. So I hope to keep this lecture a bit shorter, the following lecture a bit shorter. I'll try to aim to end this lecture in about 40 minutes or so. And so then I hope they can take the last 10 minutes after this lecture would not be introducing any new math, would not be introducing new math or anything. It's just going to be a kind of a reflection on what we achieved for the classic algorithm so far. I hope to keep it to about 40 minutes, and then I hope you can take the last 10 minutes to play around with the hands-on that you've been given. Oh, yeah. Okay. So I'm going to be sharing my screen now. Okay. So I think a big part. Okay, so the reason why we chose this point to go through the current landscape for quantum computing is because you've just passed through, I think, a a vast majority of a vast majority of the classic quantum algorithms uh that people have seen, that people have talked about. And these are all the very nice quantifiable problems that nice quantifiable problems that the field of quantum computing kind of works with. You've gone through the Dutch algorithm, the Dutch Josa algorithm, a very artificial problem with a very obvious exponential speed up that doesn't that will not translate to any real life impact. You've gone through quantum phase estimation. You've gone through quantum Fourier transform. It's and one of its kind of like one of the technique that uses quantum Fourier transform, which is quantum phase estimation. And then after quantum phase estimation, we very briefly went through Shaw's algorithm, and you kind of seen how there's been an exponential speed up for that. Today, we went through the last classic algorithm, which is Grover's algorithm, and by doing so, you have learned a new technique called the amplitude amplification, about flipping the phase, increasing amplitude, flipping the phase, increasing amplitude. You have learned a lot of different subroutines. You have learned a lot of different techniques that kind of enable a lot of this, and you see that many of them are actually common to both Grover's and QBE and a lot of these algorithms. You get superposition, you get parallelism is a very big part of this. You get phase kickback is basically apparent everywhere. And so now we thought it would be a good time to start talking about where we are at now. Okay. So these algorithms that we have gone through are stuff that we like to call the classic quantum algorithms. It's just a bit of fun you have, because saying classic quantum algorithms sometimes confuses people and says this is classical algorithms. But these are the classic quantum algorithms that people always think about when they are talking about quantum advantage, because these are the easily quantifiable ones. Shaw's provides exponential, Grover's provide quadratic. More specifically, however, you will see that the classes of quantum algorithms out there largely fall into two categories. That is motivated by by the algorithms that you uh heard last 2 days. Instead of Shaw's, I like you all to view it as either QP or QFT, and the usual speed up for it is usually exponential. Instead of Grover's providing a quadratic speedup, I hope that you recognize that it's the particular technique of amplitude amplification that helps to provide this quadratic speedup. However, I want you all to take and think about it for a second. We did the resource estimation for Shaw's algorithm yesterday. We didn't do the resource estimation for Grover's algorithm today, but we did show that there could be smart ways of implementing Grover's algorithm with the oracle. But research have shown basically that you require many qubits in order to implement RSA or to implement amplitude amplification or quantum amplitude amplification techniques. One of these is like quantum amplitude estimation. I've posted basically two papers here that are actually very popular papers in terms of resource estimation. The paper on the left is the one where the common thought of RSA providing advantage in 20 million qubits actually comes from. More specifically, however, if you just kind of go slightly deeper into the abstract rather than just look at the title, you can see that over here, they tell you exactly how many logical qubits they want to use, how many Toffoli gates they want to use. So Toffoli gates are 3-qubit gates, and the measurement depth that they will have to factor n bit RSA integers. So if you have a certain number of logical qubits is basically the fancy way of saying a qubit that is a perfect qubit. So inside your classic simulator, your logical qubit is basically perfect. The definition of logical qubit nowadays is a bit hazy because some people view it as long as the error threshold is extremely low, then it's logical. Some people view as logical qubits as just having many qubits together to form a error corrected bit. The definition kind of changes, but an easy way to think about logical qubit is basically this is the perfect qubit. This is the perfect qubit that you kind of want, and practically you can never have something perfect, and so there's something and that's where the definition gets kind of hazy. For amplitude estimation, instead, you see that for derivative pricing, on this benchmark, they realized that they will require 8,000 logical qubits and the T-depth of 54 million, which I hope you all will realize how heavy that is, because you're basically performing a 3-qubit gate 54 million times. That's when actually things start getting a bit hazy, because your operations, you have to think about how long each operation has to take when you go up to 54 million. For this particular case is also quite a lot. I mean, if you do 2000 to the power of 3, it's also no joke. Okay, so the story I just wanted to tell here is that we are not ready to, despite the theoretical advantage, the classic quantum algorithms provide no advantage at this point of time. I would like to take this moment to go through about the different types of hardware that we have. There are several considerations that one has to have for hardware. And currently, in this current landscape of quantum computing, there are several hardware limitations that we have. Firstly, is that we have too few qubits. This is a lot. This is quite interesting problem, because we see that the number of qubits increase greatly every year. But as time goes by, there might one of the issues is that increasing the number of qubits by from like 10 to 100 is still possible. From 100 to 1,000, it's going to become a lot harder. From 1,000 to 10,000, it's much harder than increasing it from 100 to 1,000. From 10,000 to 100,000, from 100,000 to a million. All of this, every exponential speed up is going to be extremely difficult to achieve. There's going to be a lot of hardware improvements that is going to be made. There's a lot of advances in technology is going to be made. Beyond just scaling the number of qubits too, you also want to think about the noise. There's too much noise, there's too much interference, decoherence, there's too much energy being lost inside the quantum systems that interferes with the operations of the quantum computers. That's a reason why you see over here 20 million qubits, noisy qubits, and instead 3n plus n log n logical qubits. It's because what they do is they kind of estimate how many qubits, how many noisy qubits it will take in order to form this number of logical qubits. Last thing is the connectivity issues between the qubits. So far, we've assumed that basically any qubit can attach to any qubit can attach to any qubit. We have mentioned that this might be a problem. This might be a problem, but the topology of the qubits is quite a huge issue because as it is quite a huge issue because in order to perform C0, a 2-qubit gate between two qubits that are not directly connected, you will have to perform several swap gates. And swap gates are expensive. You don't really want to deal with them. And so these are things that you have to think of for hardware, the hardware limitation nowadays. In order to there is a race to create the first useful quantum computer now. I've put here some of the gate-based quantum computers. There's some of the types of gate-based quantum computers that people are thinking of using right now, that people are building right now. These are the most popular types. So superconducting qubits. The advantage of superconducting qubits is that you can perform extremely fast gate operations. I think it's on the scale of nanoseconds. And so when the faster you perform you note that why this matters is because if you go back to here, you see that we have to perform like millions of operations. And so the faster you perform the operations, the faster the quantum computer will actually run, the faster you actually get a result. If all we are interested in is a time speed up, how fast you perform the operations is important. Superconducting qubits is also one of the most well understood, most well studied options of qubits out there. And actually, if you take any course in quantum information that teaches you how to build a quantum computer, chances are you'll be learning about superconducting qubits as a starting point. The problem with superconducting qubits is that generally it has limited topology. There are concerns about scaling it up exponentially because it's not going to be, because just creating the number of chips is not there's less concerns about superconducting qubits than ion trap, but it is tough. And there's also issues with the noise models. So these are not all the advantages and disadvantages. There are many more out there. I'm just going to go through a few advantages and disadvantages today. I welcome you to read up a bit more about it, but this was kind of a short summary that I was placing. The other problem with it is that it's expensive and it's energy intensive. Superconducting qubits require you to cool things down to the scale of basically it's basically you want it to be at absolute zero. Obviously, that's never really going to be the case. And currently, I think the refrigerator brings it down to the scale of like 5 millikelvins, which is still actually far too hot for it's actually far too hot to actually to be a noiseless quantum computer. That all that 1% noise error fidelity noise that you see inside down there is all caused because it's not cold enough. And this energy and this cooling is extremely energy intensive. The companies that are working in superconducting qubits, one of the most famous ones and very big in the field, IBM Quantum. Another one that is available on AWS Bracket is Rigetti. They all work with superconducting qubits. The second type of qubits, which I think that is also actually pretty well understood, is ion trap qubits. The good thing about them, ion trap qubits, is that they have extremely high fidelity. Error rate for ion trap qubits is amazing. It has an extremely long coherence. It has an extremely long coherence time. Superconducting qubits dies in a second. Well, even less than that. Ion trap qubits can last a really long time and also has a fully connected topology. The problem with it is that it's the hardest to scale so far with a lot of engineering challenges behind it. And the other problem is that operations for ion trap qubits are extremely slow in comparison compared to superconducting qubits. And when you start scaling up your number of operations to the millions, to the billions, the slow operations. Okay, what is fast? What is fast and what is slow? Okay, so to give example of fast and slow. Okay, so I this is all pretty vague here. Okay, 1 nanosecond I think is superconducting. Ion trap I think was ion trap I think was not on this
I think it's millisecond scale, right? If
yeah,
I remember correctly.
yeah, if I remember correctly, it's millisecond. I think that I remember reading some stuff that it's not so that some people managed to implement it in microseconds, if I remember correctly.
Okay.
Yeah, which is still in micro no, is it? Yeah, microseconds. I think 10 to the power of -6 is microseconds, yes.
Yes, yeah.
Microseconds, yes. So it's still about 1,000 times more slower than uh the superconducting qubits. Every scale of 10 is about things. Nano is 10
I think the latest ion Q and like continuum stuff, they're at the
yeah.
tens of microseconds, maybe something like that. But I'd have to
Yeah.
check.
Yeah. I have to check. So previously it was milliseconds. I think some of the latest research I've seen on ion trap is in microseconds. In superconducting, everything is in nanoseconds, and so that is basically a times 1,000 speed up, which is pretty significant which is pretty significant because it basically means you can perform billions of operations on superconducting qubits in the same time you can perform millions of operations on ion trap qubits. Obviously, this comes with the caveat that ion trap qubits has a much longer coherence time, whereas superconducting qubits die really fast. So, I mean, let's say advantages, disadvantages. So IonQ is one of the famous examples for ion trap qubits. It is also available on AWS Bracket. Neutral atoms is where things okay. So ion trap also probably doesn't require millikelvin temperatures as far as I remember. It's much more scalable and has fully connected topology. The problems with it right now is that it's one of the newer forms of gate-based quantum computers that have come out. So obviously it's still a bit more immature. Gate operations are slow as what they do is they physically move the qubits in order to entangle them. and because they are not as well understood yet, the technology is still slightly more immature. The gate fidelities are not as high as ion trapped or superconducting at this point, although they do expect that to change in the future. QEra is one example of a neutral atom company that does this. The last type that I'm just going to go through today is something called photonic. It's the photonic gate-based quantum computers. It doesn't require millikelvin. Okay, I put Pascal as neutral atoms. Actually, I think it's photonic actually. Football. I need to go and check again. I might have put Pascal in the wrong one. But so photonic it also doesn't require millikelvin. I think a lot of these still require cooling, actually. A lot of these require cooling, but they just don't require millikelvin temperatures. And if we can integrate it with, and the good part about photonic technology is that it can be integrated with optical communication technology nowadays. We understand pretty well how to create optical communication technology. Pascal is neutral. Psi quantum is photonic. Yeah, psi quantum. Yeah, I remember psi quantum. Okay, yeah. The control is limited. The control for photonic right now is quite hard because performing control gates on basically photons is extremely difficult. Is a huge issue that they're still trying to solve inside the photonic gate-based quantum gate-based community. There are many interesting ways of doing it with squeeze states. Squeeze states that Xanadu has came up with. I encourage you all to look through that. But it doesn't change the fact that it is currently fairly limited and it's quite challenging because photons are difficult. Yeah, Pascal, you wanted to.
I was just gonna go back to Jess's question, which is, do we know the best approach? And the answer is no. That's why there's such technological diversity. The biggest, let's say, unknown is also how each will scale up in a functional way. So the example could be if you can physically only construct something that contains 100 qubits, then you have to start then transporting entanglement across to the other unit that contains 100 qubits. That is a whole other set of problems because it involves quantum networking and moving entanglement. So it's a very open question. That's why there's like you'll see tons of new startups. There's I mean the list that Jonas put up, that's an incomplete list, right? Like the Xanadu, there's Orca, there's like Ringeti we have there, but there's also like Dirac, there's a bunch of other places. There's lots of companies trying different technologies. As a user, just to point out, the idea would be if you're trying to look at what quantum algorithms are, you would try to develop something, but the idea would be there might be limitations because some things might not be, let's say you rely on many types of a specific gate. They will obviously break it down to the universal gates that they actually fully implement, but that might be one of the noisiest gates. So then if you ran the emulation on that type of hardware, you might be like, oh, I can't run my algorithm. That does not mean that the algorithm cannot run. It's possible that another hardware would be better designed for the operations that you're trying to do and the depth you're trying to do, and other ones might be better. So there's a lot of open-ended problems with open, and that's why there's such a huge amount of technological diversity.
Yeah. So Jess also, I think Pascal answered basically Jess's question. What's the best way to approach? Is everything very balanced with advantages and disadvantages? Rather than calling it balanced with advantages and disadvantages, I would say that the technology overall on the whole is just so immature that we are too early in the race to even figure out who's leading the race. We can only talk about current advantages and disadvantages. Some disadvantages might disappear over time. Some advantages might appear over time. Some advantages and disadvantages might appear over time. Who knows? Who knows really?
A good analogy would also be that it's not just the hardware, it's also the access to the hardware. So VHS and Betamax way back when you had cassette tapes, right? They were two formats. Betamax was better, but they didn't go open source so that everybody could just grab VHS. VHS maybe worse quality, but gave everybody access, made it easy to use. And so now for the brief while that we had tapes, VHS was the only thing. Betamax went away. So the same thing might happen here. You might have a technology that's slightly more performant, but I think most companies are trying to make sure that they also anybody can muck around with them to try to make it as open source as possible. Hold on. It says, I've noticed one of the consequences has a unidirectional 2-qubit gates. Okay, what are the
It's
consequences? Oh,
okay.
go ahead.
So the short answer for this one, this is a problem not just for the Oxford device, but the Lucy device for Oxford. It's a problem for basically for any quantum computer. If you don't have a fully connected topology, it's the software on the software side of things, you're going to need a transpiler to handle it for it. Because you, to a certain extent, you want to be able to just create a circuit without worrying about the topology every single moment. You don't want to be like tailoring your circuit every single one. And so you want a systematic way to do it. And that's where transpilers come in, and that's where this very active area of quantum software research is currently coming in. Yeah, but actually nowadays, when people are trying to trying to squeeze out every single bit of advantage from a certain quantum computer, some of them really do design this circuit with the topology in mind.
Yeah, that's what I was gonna say. Like the
Yeah,
idea of being topology agnostic, like this idea of 10 qubits being entangled actually at all together, uh, as long as there's enough, like fully connected, fine, that's fine. If it's partial, uh, that could, in principle, limit what you can run on there, unless the translation process is really fantastic, to
yeah,
try to figure out how to translate what you've asked for to the gates that can be implemented on the computer. Sorry, on the actual device.
yeah,
Right now, uh, that's why there's so many places that have conversations with you for their hardware, is that you cannot be completely topology or hardware agnostic. You
yeah,
have to have a conversation. The transpilation process, well, I should say for simple circuits, it's kind of trivial. It's for complex circuits, real circuits that you're trying to solve a problem. That transpilation process is itself also not, is still a work in progress. And so that's why there's conversations about what you're trying to
yeah,
achieve given certain set of circuits.
yeah. It's still a very interesting this transpilation is still a very interesting uh space because different types of qubits the different types of qubits also you also want to do different that will be tailored to different problems as well. It's kind of uh interesting. Yeah. Sorry.
I,
Someone message Diction message. Okay.
Yeah. I'll just quickly on the note, right? So the idea that there might also be like truly one technology that takes over is not true. If you even look at so
Yeah.
we all have silicon chips, but there's GPUs, there's APUs, there's TPUs, there's TPUs,
Yeah.
right? Data processing units. So even if they might have the same underlying technology, the specifications change.
Yeah.
Here, the idea is that also you might have a couple of different underlying technologies. They just end up being viable, and you just have to pick one,
Yeah.
or maybe pick a few to solve possibly the entire breadth of problems.
Yeah. So I know a lot of the answers that we are giving right now might sound a bit frustratingly vague, but which is why I would like to just go back a point. We are currently early in the race to even figure out to really have a good prediction on what will happen at the end. Things could change. At, things. What does unidirectionality mean in terms of context of topology? I don't think I understand that. Okay, so it basically means you can do the control target. Unidirectional means you can do your control target one way but not the other. Bidirectional means you can do the control target both ways. Okay, yeah. Okay, so I've put up, okay, so here are some of the development roadmaps for the different ones. So IBM, this is their development roadmap all the way until past 2033. Uh, you can see right now they recently released the 133 qubits one that is supposedly very low error rates, and they also recently released a 1,000 qubit quantum computer. I have not seen the specifications for that one yet. I do need to get on that check. And then you can see that they are currently trying to go and do a much higher circuit depth. I know this is really very small, but you can go and Google this development roadmap if you're interested yourself. And you can see it goes all the way to 2000 qubits over here, and they are hoping to include thousands of logical qubits by 2033. It's extremely, extremely ambitious. I don't know how true that I look forward to see how true this is.
So just on the IBM node, you'll notice that there's pathways where they just have bigger, like Condor is essentially just a bigger
Yeah.
circuit with more superconducting qubits that can be used as logical qubits. But the Heron architecture is one where they're trying to do more modular stuff with entanglement across.
Yeah.
So that's one way they're trying to maybe scale up to huge
Yeah.
amounts of qubits.
Yeah. So yeah. Okay. So I'm not going to go through. So IonQ also has a roadmap. This was one of the posts that they made. Instead of, because they can't really compare on qubits and stuff like that on qubits as much, they try to do it of this thing called, they create their own benchmark called a algorithmic qubit. I'm not exactly sure what that means, to be entirely honest, but yeah, this is one of the examples of how hardware might kind of change how you approach your different benchmarks. And this is the benchmark they came up with. I don't know how. I don't actually know. I don't work with ion trap qubits enough to know what this really stands for. And I
I'll
think
just hold on, Jonas, do you mind if I mention quickly
yeah,
that if anybody's looking, they'll also notice that some companies will definitely choose different ways of benchmarking the systems. There's not let's say a lot of agreement. Some of it might be, I think the AQ one is fidelity, folds in fidelity at some point. So that it's not just a qubit measure, but it's like supposed to measure like, well, some measurement of truly functional perfect logical qubits as opposed to qubits. But I can't remember the details.
Yeah, I don't remember. There's a lot. Okay, so here's one of the problems. Okay, I mean, since you touched on this, okay, we are going to go slightly faster, but one of the problems also you mentioned over here, which is why actually NIST has been trying to ask for standardizations in quantum computing, because everyone is kind of really coming out with their own benchmarks in order to say that their stuff is good. So yeah, I mean, they're playing around with benchmarks for marketing purposes also tends to contribute a little bit to the hype. It can be detrimental in some cases, but the companies have to do what they have to do in order to try to promote their hardware. Because they all believe in the product. You don't work on superconducting qubit believing that the superconducting qubit will not at least come out pretty ahead in the race. They all believe that their type of computer will be the best, and I mean, will the one to win the race, which is why they're working on it in the first place. You have to have that belief when you're going into it. It's easier for us, people in the software field, because we go like, we'll just wait to see what happens. We'll just wait to see what happens. We'll wait to see what comes out. We'll try to work with we'll just work with what we have and see what types of problems come out of it, and that's all very interesting to us. But the hardware people have to believe in what they do, because they all okay. QERA is another one. So currently they are one. I put neutral atoms, but currently what they are neutral atoms is really more of an analog quantum computer. I'm going to be talking about what that means. So Aquila is really more of an analog quantum computer, but they do plan to try to add that layer of abstraction to make this gate-based in the future. So you can see this logical qubits. And they want to progress really fast, because like moving from 256 to over 10,000 physical qubits in 3 years sounds a bit crazy to me. But yeah. So you can see that all of these are moving really fast. If you want to do like an exponential scale, it means that we'll probably break Shaw's by 2030, really. But who knows? Okay. QERA, photonic quantum goals are coming. So PsiQuantum has a goal for million qubits. So does Xanadu. I don't know about this. This also seems like a bit of a crazy goal in mind. PsiQuantum came out with this million qubit one. This article was released in like 2022, at least. Xanadu is a bit more realistic about the timelines whenever I have conversations with them. I have not had the opportunity to have a deep conversation with PsiQuantum at this point, but I have had many conversations with them too. They are very realistic that this is kind of like their long-term goal and not the short-term one. But they don't really have a roadmap. I was looking for a roadmap. They didn't really post a roadmap for it.
They don't have one.
Yeah.
I mean, in Cyclone, I don't think there's an actual roadmap. They just have a bold claim that they're gonna have 1 million photonic qubits.
Yeah. So yeah, and these are just the most of these projections are stretch goals. You are right. These are these are things that they tell investors so that a lot of these are more ambitious than what is probably going to happen.
So the ones that are maybe a bit more realistic is that if you take some of the like IonQ and QEra and even IBM, they're aiming for, you know, tens to hundreds of logical qubits within some time scale that they feel like they've got already the technological base to kind of get there. Now the main question might be actually like whether they should end up being logical qubits. You might be able to manufacture something with like 1,000 physical qubits, but it's possible that at a gate depth of 10,000, you might be like, it's 50 qubits, right? That you're gonna get. So the error correction stuff is also a big deal.
Yeah.
And I'd say they're probably all ambitious roadmaps, but some of them are crazy. I personally think, like, I don't know how you're going to achieve that, but the other ones are maybe a bit more realistic. So the IBMs and QEra and IonQ and so on, they're probably more in the realistic, if ambitious scale.
I'm just a lot of these things. I will just put this out there as well. A lot of these things that they come and put out here, a lot of it just come with caveats as well. They just don't tell you the bad statistics that probably come along with them, like the noise or something like that. So take all of these roadmaps with a grain of salt. Take all these roadmaps with a grain of salt, but it's pretty interesting to just see how many of them, what they are trying to aim for the future. This is not and there are many other types of quantum hardware as well. There are quantum annealers. Many of you have heard of systems that kind of like, oh, I have done like things on 5,000 qubits. There is a huge debate on whether quantum annealers are actually quantum computers. Quantum annealers are basically hardware that works on different quantum phenomena, as I think I mentioned yesterday. Currently, Advantage system has about 5,000 qubits. But it's really only good for one type of problem and one type of problem only, which is the quadratic unconstrained binary optimization problems, QBO problems.
I would think and I think most people, they're not really quantum computers because they don't implement gates and they can solve essentially a very specific set of problems. But that's still like useful. It's just you wouldn't necessarily be able to generalize them in any way. You have a problem, it has to be posed this way, and then it can try to solve it.
Okay. The other type of to what extent can classical computers simulate QCs, for example, how many qubits simulate? This is a interesting question. Okay, so I did not put any of that in these slides. Maybe I should have, but so if you're talking about there are 3 different types of simulators around: state vector simulators, density matrix simulators, and tensor network simulators. And you'll notice that, and if these sound familiar, it means that you probably remember these stuff from the Rajesh's talk, I think, on the first day. He went through the different type of simulators that they have. So I'm going to classify state vector and density matrices kind of together for this, because what they can do is basically you can implement an arbitrary number of gates on them. You can implement basically what it does is it stores the state vectors, it stores every single it stores every single state. So if it has 30 qubits, it stores to the power of 30 states in their memory, and then they perform the gates and you can calculate it. It's a lot more difficult for density matrices because you are instead of storing one vector, you're storing the matrix instead. And so the current threshold for NVIDIA is really realistically in the 30s. It's in the 33 range. Why this is so is because let's say you need the supercomputer, you need like one supercomputer's worth of memory in order to store 30 qubits. It means you need two supercomputers in order to do 31 qubits, and you need four supercomputers and four supercomputers worth of memory to do 32 qubits. And so this scales, like it scales in that form. Realistically, with one supercomputer, you can probably do about 35 at this point of time, but scaling it harder basically doubles it every single point.
But you can do, so there is possibility of doing circuit cutting, and that has its own overhead where you would normally then decompose the problem and allows you to get to maybe more qubits because you can then split it across a couple of different portions of the machine, but it's complex. The tensor network simulator it's got lower memory. It's state vector stuff, the NC stuff has huge memory footprints.
Yeah. So tensor network basically works in a way where you basically work on like the operations instead. And so your memory is all in terms of operation. And so you can go into a much higher number of qubits, arbitrarily high number of qubits if you have very few operations. For each of those qubits. And so I think the most extreme example, Dikshan talked about it. Yeah, generally you do 50 to about 70 qubits with tensor networks for the experiments. That's the general things. But I've seen some where they really pushed the tensor networks to go into hundreds of qubits. But that was for like a circuit depth of like 5 gates or something like that.
I think they've done 10,000 but like as just like a big the new Grace hoppers, tons of memory, and then like the trivialist thing. Right.
Yeah. There's the most trivial things, and like imagine what can you do with like a circuit depth of 3 or 4. That's probably what you're going to get with 10,000 qubits. And you have 10,000 qubits, you can really only implement 3 or 4 circuit depth, then it's like it calls into question, is this really necessary? So most of the time you're going to be working about 50 to 70 qubits of tensor networks simulators. The last type of quantum hardware is actually to do with that I put up here an example. So there are actually other types of quantum hardwares out there. I've not mentioned them here as well. Another a very key the last one I put down here is quantum key distribution. This is actually probably the most mature form of quantum technology there is out there. And this is entirely for cybersecurity. This is entirely for communications, entirely for networking. It works based on quantum information. Entanglement and quantum information entropy matters a lot more for quantum key distribution than a lot of other ones. I think one of the biggest omissions that I couldn't really find an example for here is this thing called QRAM. I don't know of any. I know some people there's a lot of research. There was a lot of research on QRAM. Currently people have given up on it a little bit because it's just been proving a bit too difficult to create. But the whole idea of creating a quantum analog for random access memory is something that a lot of algorithms actually assume. A lot of fault tolerant quantum algorithms actually assume. And so it's a bit unfortunate that I haven't really been able to find any good examples of people working on it. Yeah. Okay. So these are just the types of quantum hardware out there. Now,
I'm going to throw in one more thing, Jonas, because you touched on it, which is that the fault tolerant, like converting a physical qubits to logical qubits with error correction and so on, the scaling of that is also a complicated thing of what technologies might be going forward, how they might be able to take truly, like they're going to be noisy systems to something at, the logical qubits. So the example is mid-circuit measurements, other stuff. Some things can do it well, some things cannot. So the error correction adds a bit more complexity to what might scale up in terms of the landscape.
Yeah. Okay. So this is the discussion around the quantum hardware. This is the current landscape for the quantum hardware. It's not great now, hopefully great in the future. If a single one of the roadmap is true, any of the roadmaps is true, is heralding good things for the future. The other part of things is on quantum error correction. This is another topic that we kind of like touch upon, browse a little bit, but not really they didn't really go into detail. So one of the most classic examples for quantum error correction in the classical computer is basically what you want to do is you have your bit, you copy it many times. In this case, just 3 times, and then and then you send over a data. And then this introduces a small chances of error, and then you just do the majority rule, where the biggest number of zeros become 0 and biggest number of ones become 1s because there's a chance of corrupting data. Now, can we do this with a quantum computer? Can we do this? No, we can't. We can't because we have the no cloning theorem. So, people have actually created smart ways of doing this type of 3-bit sequence. They utilize similar concept where this is taken from I didn't put the credits. Well, this was actually taken from my old professor's notes. She created this diagram. But you can see that it uses many qubits basically. Like you started with 1 qubit. You started with 1 qubit, and then now you have 5 qubits just to do one to protect 1 qubit. This is just for the bit flip, and you can extend it to a lot. So you can do the 3-bit flip code is basically like having basically just the three data qubits. The 3-phase flip is basically the same thing for phase. You can do things for the shorts. This feeds into shorts codes, which is 9 qubits. People have gotten smart and created the sting code and the 5-qubit error code. This one is 7 qubits to protect 1 qubit, 5 qubits to protect 1 qubit. And then people have created similar. And I think I just also want to make a note that this is all just to protect 1 qubit. We haven't even started thinking about protecting 2 qubits. You still remember we protect 1 qubit because that inside the universal gate set, I said just now there's 1 qubit gates and 2 qubit gates that we have to worry about. Yeah, when we start involving 2 qubits, you're going to have to protect against 2 qubit errors instead of just 1 qubit errors. This only protects against 1 qubit errors. And so there are many, and so you have really think about how you want to protect multiple qubits. And so there's a lot of work currently being done for quantum error correction for fault tolerant computer. And as you can see, these are all very expensive in the form of just to protect 1 qubit, I need at least 5 qubits. If I want to protect 2 qubits, I need more. And these 5 qubits don't even include the ancillary qubits that you put inside down there that you need. You still remember the 3 qubit first? You also need ancillary qubits to protect 1 qubit. And so we again return to hardware limitations because there's just too few qubits for us to work. Simply put, there's just too few qubits for us to work with in order to actually experiment too much with different quantum error correction protocols to see how well they work. And a lot of this also relies on the noise not being too high, because if the noise is too high, there's no error correction that you can do that will ever help you. That will help you too much. So there are many other error suppression schemes that people are currently coming up with. There are diagnostic techniques, gate set tomography to kind of figure out what's the problem with your gates, and then you can correct it on the hardware level. Shadow tomography is one of the interesting things that come out of gate set tomography that is to diagnose that kind of helps you diagnose your state. Error suppression is this thing called dynamical decoupling, where if your qubit is idle, there are ways to move it to prevent certain types of errors. There's post-error correction schemes. So okay, after measuring, what can I do in order to ensure that my measurement looks better? My measurement looks better. So there is quite a few schemes for this. Not going to go through any of these in detail, just to let you know. And so this just brings us to where we currently are, which is the NISQ era of this thing we call NISQ era quantum computing. I'm going to I did not change. Oh, this is the old version of the slide. Okay, so NISQ era quantum computing stands for noisy, which means error prone, and intermediate scale quantum computing. Fault tolerant, fault tolerant is basically there is no more noise on the things, and you're working on A fault-tolerant QC is basically there's no more noise. There has been some distinctions made between fault-tolerant QC as early fault-tolerant and late fault-tolerant, because we're expecting that even with like 50 non-error-prone qubits, there are things that we can do, and this goes to late fault-tolerant where you go up to millions of qubits. So the real question with the NISQ era quantum computing right now is the real question that people are asking is, can we do anything that how can we utilize current quantum computers and whether they can generate value right now. And so this brings us to the variational algorithms, which you have heard one of yesterday, and you will hear a bit more about later. Dikshan will be going through VQE later, and this will be for you heard about QAOA, you heard about VQE, you're going to go through some QNNs, you're going to go through some simulations later. A lot of these things are variation methods that were proposed in order to make NISQ era quantum computers useful. Okay, so I think an important thing to note is that for variational techniques is that any technique that you create now, you also want to make sure that it will be useful in the fault-tolerant era. Okay, because you don't want to be creating something that is useful just for now with noisy quantum computers, and then not have it not be useful in fault-tolerant. Chances are, if it's useful now, it's also going to be useful in fault-tolerant, to be honest. And it all depends on how you define unuseful. Is it useful in terms of a proof of concept, or is it useful in terms of actually having a business use case? One last consideration that you will have to have is that currently I've described a little bit on what's happening in the hardware side and the software side. A lot of work is also being done on the middleware side, where it's trying to enable, to a certain extent, the proliferation of quantum computing the success of quantum computing has to do with the proliferation of quantum computing. Proliferation of quantum computing. And the more middleware there is to enable this proliferation of quantum computing is going to be key to ensuring the success. That's why cloud systems like AWS Bracket, like the IBM Quantum, is very important. That's why governmental support it's very important. That's why people thinking about, should we do it with on-premise systems? What are the connections to quantum computing? Making sure that everything flows seamlessly together, because quantum computing is not going to replace classical computing. It's going to have to work with classical computing at some point in the future. So yeah, so this is the landscape for quantum computing so far. I hope that I introduced many interesting very interesting conversations over here about the different quantum technologies there are, the different areas of research people are looking at. And yeah, I hope that you can appreciate how far we've come from just those few concepts and how much more we need to do.